All right, number 13. All right, so in this problem, we are integrating from negative infinity to positive infinity, so over the entire real number line. Fortunately, this function does not have any discontinuities. I could rewrite that as this, and the denominator is never 0. So we're good to go. We can just integrate. But the way we do this is we actually break it up. So we're going to go over the entire number line, all the way out this direction, all the way out this direction, everything in between. What we'll do is split it into two integrals, and I can split it anywhere I want. I could split it at 2, at 5, at -10, but the most natural place to split it would be at 0. So we're going to basically find the area on this side and this side, add the two areas together. So this integral becomes integral from negative infinity to 0 of x e to the negative x squared dx plus the integral from 0 to infinity of x e to the negative x squared dx. All right. Now, I'm going to need the antiderivative of that, so I'm going to work on that right here. This is a basic u sub. U is negative x squared. Did he knock? I saw him. I didn't hear any knocking. Derivative of this is negative 2x dx. We have an x dx off by -2, so scale that out. And so this becomes integral -1/2 e to the u du. So replace that with u. X dx gets replaced with -1/2 du. And the antiderivative of this, of course, is itself plus a constant, which is equal to -1/2 e to the negative x squared. So that's the antiderivative. And so now I'm going to come back over here. I'm actually going to have to set up two separate limits. So maybe I'll put this up here. We're going to have this first one, which will be the limit as t goes to negative infinity of we're going to go ahead and do the antiderivative. Antiderivative of this, which is this, -1/2 e to the negative x squared, evaluated from negative infinity, which is my t, up to 0, and then plus another limit as t goes to positive infinity this time of the antiderivative of this, which is still this, evaluated this time from 0 to infinity, but infinity is my t. So that's it right there. Now, each one of these requires that I plug in 0, then t, and subtract, and then plug in t, and plug in 0, and subtract, and then take my limits. Notice the limits are going two different places, though. Negative infinity here, positive infinity here. So let's see if that changes anything or how that affects things. Limit t goes to negative infinity, and then I'm going to have two things in there. So first let's plug in 0. 0 squared 0, -0 is still 0, e to the 0 is 1. -1/2 times 1 is -1/2. And then we plug in t. Let me give myself a little more room here. Plug in t, get -1/2 e to the negative t squared. Then we have plus limit t goes to positive infinity this time of two things subtracted here. So we plug in t first, get -1/2 e to the negative t squared. And then we plug in 0, we get the same thing we got over there, -1/2. All right, let's plug in negative infinity. And we're going to plug it in for t here. So if I take a negative number and square it, it's positive. So a very large negative number squared is going to be a very large positive number. So this right here is headed towards positive infinity, but then there's a negative in front of it, so that makes it negative infinity. So we have e raised to the negative infinity, which I just showed you in a previous problem, that goes to 0. So this thing goes to 0, and that thing doesn't matter. The whole thing goes to 0, so all I have is -1/2 here. Plus, now over here, same sort of thing. I'm plugging in infinity in for t, and I'm squaring it, so I'm going to get positive infinity. Then I'm subtracting it, so I get negative infinity, and then e raised to that, and that goes to 0. and then the whole thing goes to 0. And then over here we get minus is plus, so you get plus a half, which is equal to, if you add these two together, you get 0. So we get 0 as our total area for that one. Kind of interesting. I wonder if it has, if I have time to show the graph of that one up here. What number was that? 15. Yeah.
When you have the integrals before you split them up, you distribute the negative. So it'll be like negative x over such and such and plus 1 over.
Where are you looking? Yeah, if you're going to distribute the negative, but where did the negative come from?
From negative 1. Because they're both negative.
They're both negative. Then put a plus there. Put a plus. Make that a plus, and then put a negative on that one. And then you could pull a negative out of both if you want.
Okay.
And then make it a minus.
All right, thank you.
What was this? I don't know if I have time to graph this. But I won't. But essentially what's happening is that the area, part of the graph is above the x-axis, part of it's below, and those areas together wipe each other out, and you get a net area of 0. All right, let's take a look at 15. Okay, for 15, we have integral negative infinity to 0 of z e to the 2z dz. All right, so I'm going to start by just making sure I don't have any issues. I'm looking from 0 to the left. This function doesn't have any discontinuities, so it should be okay to integrate without any issues. But I need the antiderivative of that, and that's going to be where I'm going to run into some issues. So this, if you look at this, this does not work with basic substitution. If you let u be this, the derivative of that's just 2. That's a z. That doesn't work. Also, notice I'm striking my z's. I recommend you strike your z's so you don't confuse them with 2's. Okay, so you look at that a little bit and then you go, oh, wait a minute, hold on. I've seen something like this before. Integration by parts. If I let u be the z, I know that in the new integral it's going to be a 1, or dz. And then dv would have to be the other part, which is e to the 2z dz. And I should be able to integrate this. So integrating from here to here, I'm not going to show that. Everyone should know how to do that at some point here, or by this time you should be able to integrate that. It's itself, but then you have to scale out the 2, so you put a 1/2 in front. And then over here you get du is dz. And then the ultraviolet minus voodoo, the voodoo part of it is nice, because when you put these two together, you don't have that z anymore. So this becomes ultraviolet, which is z times this, so 1/2 z e to the 2z minus integral this times this, so 1/2's coming out, e to the 2z dz. And then to integrate this, well, you already did that. From here to here was an integration, so it's going to be this again with a 1/2 that's going to pop out. So we get 1/2 z e to the 2z, and then minus 1/4 e to the 2z. So that 1/2 that came out joined up with this one. These both have an e to the 2z in them, so I'm going to factor out an e to the 2z and be left with 1/2 z minus 1/4, like that. All right, I think that that's good. All right, so back here. This will be equal to the limit as t approaches negative infinity of this antiderivative, e to the 2z times 1/2 z minus 1/4, and then evaluated negative, or sorry, not negative infinity, that's my t, up to 0. And now I'll plug in the two values. Limit t goes to negative infinity of, and then I'll have two things here. So we plug in 0. E to the 0 is 1, and then 0, then minus 1/4. And then over here we plug in t, so we get e to the 2t times 1/2 t minus 1/4, like that. All right, now at this point I need to plug in negative infinity. So what's going to happen here? This is rather tricky problem at this point because I need to figure out what happens to this. If I let t become negative infinity, 2 times negative infinity is still negative infinity. So that first piece right there looks like e to the negative infinity. Now we already know that that goes to 0. The problem is that we're multiplying that times this, and half of negative infinity is still negative infinity, and infinity take away 1/4, you're still negative infinity. So you've got something like 0 times negative infinity. And that is still an indeterminate form. We do not know what that turns into. We have to do more with this. So this is something that we ran into, hopefully you ran into in Calculus 1. So what I'm going to do is try and remember what this was. This was negative 1/4, this first one. And then I need to figure out this limit. I'm going to subtract it. So subtract whatever this limit is. The limit is t goes to negative infinity of e to the 2t times 1/2 t minus 1/4. All right, so let's see. Anytime we get that, 0 times infinity, whenever we ran into that in Cal 1, or if we had 0 times negative infinity, it didn't matter. What we need to do is pick one of them and drop it down and make a fraction, make a ratio out of it. So I'm going to rewrite this as limit t goes to negative infinity. I'm going to choose to drop this one down. So I'm going to leave 1/2 t minus 4th over, and then I'm going to write e to the negative 2t. And now let's just double check to see what happens. If t goes to negative infinity, then this becomes negative infinity minus 1/4. That top is still going to negative infinity. But now on the bottom, something different happens. Negative infinity here, if you take a negative 2 times another negative number, that's a positive number. So now the bottom's going to e to the positive infinity, which blows up. That becomes infinite. So this is over infinity. Anytime we have infinity over infinity, we can apply L'Hopital's rule. So that's the key to dropping that down, is that it'll create this form. So this, by L'Hopital's rule, and people do it different ways. I do an L, some people do an H, just to let everyone know they're about to use L'Hopital's rule. If you don't remember L'Hopital's rule, please look it up in the book. There's a whole section on it. I've got videos on it. Oh, I didn't do the rule. The rule says you just take derivative of the top and derivative of the bottom. So the derivative of the top is just 1/2. And the derivative of the bottom is the derivative of this. So derivative of e to anything is itself times the derivative of what's up here, negative 2. And then what you do is you reapply the limit. So as t goes to infinity, nothing happens up here. We just get 1/2 on top. But the bottom, again, the negative and the negative together become a positive, and this is e to the positive infinity. That's going to become huge times negative 2. It's still huge. This thing is becoming infinite. And, well, it's actually negative, but it doesn't matter. You have a fixed number over infinity. That thing goes to 0. So what I know is that this whole limit right here goes to 0, which means that my answer is negative 1/4. Interesting. You have all that for nothing. Well, we got negative 1/4 though. That was still good. You got more, or are you okay? Or
I'm just gonna practice now.
okay,
More.
okay.
Do you mind if I take a look out of your book?
Yeah, go ahead. Let me write the next problem down, and I'll work on that while you look at the book. Yeah, y'all don't have anything due this week, right? Yeah, take this time to catch up, or to get on, get everything in order. 17, integral 1 to infinity, natural log x for x dx. If you have a piece of paper, do you mind like sticking a piece of paper in here so I can flip back to it real quick? Okay, on this one, integrating from 1 out to infinity, the only discontinuity I have is actually at 1. That's the only, I'm sorry, not 1. At 0 is where we get undefined on the bottom. At 1, the top is 0, but the bottom is 1, so that's okay. So from 1 to the right, this thing is defined. We're in good shape. So I need to integrate that thing. And I realize I can make a basic substitution. The derivative of that is 1 over x dx, which I have here, right, if I rewrote this. That's the same problem. So this is just going to become integral u du. That's pretty simple. That doesn't get much easier than that. So 1/2 u squared is the antiderivative, which is going to be 1/2 natural log of x. That quantity squared. So be careful, we're not squaring the x, we're squaring the natural log. So this becomes the limit as t goes to infinity of the antiderivative, which is that, 1/2 natural log x squared, evaluated, let's see, 1 in t, which is the limit as t goes to infinity of, and then we have two things here. So first plug in t, 1/2 natural log t, that quantity squared. And then let's see, if we plug in 1, natural log of 1 is 0. So that's nice. And then let t go to infinity. If you let t go to infinity here, natural log of infinity gets big and blows up. Squaring it blows it up. 1/2 times that still blows up. This thing is infinite, so it diverges.
The assignment was 1 through 41, right?
I don't recall.
It was all of them.
Let's see. is, there it is. All right, so on this one, we do need to be a little careful because there is a possibility that the denominator could be 0. So let me talk about that. If I factor that, I get two solutions, 0 and -1. And fortunately for us, we're integrating from 1 to infinity this way, and both of the zeros that we have are here and here. So we don't have any discontinuities in the interval that we're integrating over. So I'm free to integrate. But to integrate that, I'm going to have to use partial fraction decomposition. So I'm going to rewrite the integral. I'm going to factor out the denominator. And then I'm going to go ahead and do my work now. I need to rewrite this as a over x plus b over x plus 1. And then 1 equals a times x plus 1 plus bx. And then this is one of those ones you can do the short method on. If I let x be equal to 0, I get 1 equals a. That killed off this one. If I let x be equal to -1, then you're going to get 1 equals -b, so b is -1. So this integral turns into a over x, which is 1 over x, plus b over -1 over x plus 1 dx. And the antiderivative here is pretty clean. It's natural log, absolute value of x. I'll bring the -1 out front, -1 natural log x plus 1. All right, good to go there now. So we come back over here. We set up our limit as t goes to infinity of this antiderivative, which is that thing, 1 over x minus, the antiderivative, natural log of x minus the natural log of x plus 1, evaluated 1 to t. Ooh, this could be a little tricky here. I can already see what's going to happen. Just thinking ahead here. When t goes to infinity and I plug that in, I'm going to get natural log of infinity minus natural log of infinity. So you get like infinity minus infinity, which is not a good situation. So before I proceed, I'm just going to use a property of logs here. And if we have subtraction between two logs, we can turn it into a single log and turn it into division. So x over x plus 1 instead. And what's good about that is when I do plug in the t and I get infinity over infinity, I can use L'Hopital's rule. But I'll deal with that in a second. So that's where we're at. And now this turns into two pieces. So limit t goes to infinity of, got two things being subtracted here. So first let's plug in t. You get natural log t over t plus 1. Then we plug in 1, you get natural log of 1 over 1 plus 1 is 2, so 1/2. All right, when we let this limit t go to infinity, we get infinity over infinity. We need to figure out what that is. So real quick, limit t goes to infinity, t over t plus 1 equals, by L'Hopital's rule, limit t goes to infinity. Derivative of the top is 1, derivative of the bottom is 1, so the answer is just 1. So this is going to 1 in here, and then natural log of 1 is 0. So you get 0 here, and then you get minus natural log of 1/2. And that would be the answer. Although you can move the negative up as a power, like a -1 on that. And when you have a negative power, -1 power on a fraction, it flips it. So you can get natural log 2 as your answer. What number was that? Okay, so we're on 21 now. Ooh, 21 looks fun. How you doing?
Did you ask them to use
Yeah, I did. Why?
I don't know, because that lady was looking at me funny when I was coming in here. and
Oh.
Pointing.
Yeah. Yeah, they don't, I don't know why. This room is totally underutilized. Like it doesn't get, it doesn't get used the way it's supposed to be used. But then when I ask to use it for something like this, they're like, well, I don't know. And it's like, nobody's in here. That other conference room, they're having we have a group, a committee that's visiting the campus today. And it's for our accreditation. It's the Southern Association of Community Colleges, blah, blah, blah. And they basically, once every few years, come out and evaluate the college and then give us the approval stamp that we're an accredited college. And they're here this week. So that conference room that I usually use is all set up. That's why they were cleaning it up last week, because they're getting ready for this big visit. So.
So do they go to each professor?
No. In fact, the last, I don't think I've ever talked with them when they're here. But there's always the potential where they could just walk in and be like, hey, and start asking you questions. And so, yeah. Where did my marker go? All right, you good? You have a question?
I'm just working from.
Okay. Let me know if you need anything. I'm getting kind of burnt out on these here. Negative infinity to infinity. X squared over 9 plus x to the 6th dx. How's it going? You found us.
Yeah.
Yeah, I figured it might be hard to find this room. Make yourself at home anywhere. I'm working problems from the next homework assignment right now. He's doing partial fraction problems, and after I finish this problem, I'll help you out if you have any questions. Okay, I'm going to need to integrate that. There's no discontinuities here. The denominator can never be 0, so I don't have to worry about anything in terms of discontinuities. But since I'm going from negative infinity to infinity, I will need to split this into 2 integrals. But the overriding thing is I'm going to have to find the antiderivative of that. So let me do that right here. So I see something here that x to the 6th was kind of a problem, but it's actually going to be a good thing because x to the 6th is x cubed squared. And if I let u be equal to x cubed, the derivative, 3x squared dx, I almost have right here. So I'm off by a constant, and that's okay. And so I can rewrite this integral. The x squared dx is this, so I'm going to have a 1/3 du. Over here, this x squared dx is gone. I have a 1 over 9 plus, and then this x cubed was u, so u squared. And that, I hope that you would recognize, is going to require arctangent. That's just a formula. So this becomes 1/3 times, now for us, this is a squared, which means a is 3. So the formula for arctangent is 1 over a, arctangent of u over a, and that's going to be 1/9 arctangent of u over a, but u is x cubed, so x cubed over 3. That's the antiderivative. And then back over here. So this becomes, split it up first into 2 integrals. I'll go to 0. Then from 0, I'll go to infinity. And then each one of those turns into a limit. So we've got limit t goes to negative infinity of, let's see here, the antiderivative of this, which is 1/9 arctangent. I'll give myself a little more room. X cubed over 3 evaluated from t to 0. So I've got to figure out what that is. Then I've got to go plus limit, this time t is going to go to positive infinity, of the same antiderivative, 1/9 arctangent x cubed over 3, this time going from 0 to t. All right. So I'm going to get two things out of this. I think that's enough room. Limit t goes to negative infinity of, let's see, this minus this. Then I'll have another one, but let me do this one first. If I plug 0 in, I get 0 here. Arctangent of 0 is 0. And then times 1/9, it doesn't matter. So, okay, that whole thing is 0 right here, this first one. Minus, now I plug in t, so I can't really do anything with that. So 1/9 arctangent of t cubed over 3. And then I'll do this limit. So limit t goes to positive infinity of, again, two things. I know when I plug in t, I just get that expression again. When I plug in 0, I did that over there, I'm going to get the 0 again. And now I'm going to take the limit. Is that my phone? Okay. Take the limit again. All right. If I plug in negative infinity in here, a negative number cubed is still negative. So I get negative infinity on top over 3, it's still negative infinity. So the question becomes, what is arctangent of negative infinity? Well, to understand what's happening here, you go back and you look at the tangent function. This is tangent of x. And tangent of x has vertical asymptotes at pi over 2 and negative pi over 2. So when you say, what's the inverse tangent of negative infinity, you're saying at what angle do you get negative infinity out of the tangent function? And we know we can never do it, but it's a limit. That's what is it approaching? So to get negative infinity, we come down like this. That happens when x is negative pi over 2. So this right here is going to turn into negative pi over 2. So I have equals, the 0's gone, negative 1/9 times, and I just said that this piece right here is negative pi over 2. So that takes care of that. Now over here, same thing, but this time going to positive infinity. Positive infinity cubed is still positive infinity. So this time you're asking, what is arctangent of positive infinity? And that's going to be this side right here. So you go to positive infinity, that happens at pi over 2. So this thing is pi over 2. So this will turn into plus 1/9 times this, which is pi over 2. And then you have 0, so it doesn't matter. And when you put these two together, these two negatives multiplied by positive, you get pi over 18 plus pi over 18, which is 2 pi over 18, which is pi over 9. So the area is pi over 9. I don't remember that being the answer, but it is. Okay. Do you have any questions, Zach? No? Did you have a good weekend, Zach? Work a lot? Do you get all that car stuff taken care of? No? All right. You worked 57 hours? Oh my gosh. Are you good? Sure. Okay. All right. 23. So I only have 1, 2, 3, 4, 5 more to go. 23. Integral 0 to 1, 3 over x to the 5th dx. Bam. All right, so
So this is kind of simple, but the limit makes it thrown off.
yeah, having that additional piece there, the integrations usually aren't as bad in this section, but it can be anything. Like I've done the first few here, and I've done integration by parts, I've done partial fraction decomposition, I've done basic substitution. So the integrals can be kind of whatever, but it's that limit stuff. Like I don't know if you just saw what I did with that arctangent.
I remember.
Yeah, so. All right, so this is the first one I've done so far that has that's the type 2, because these are not, neither one of these are going to infinity. And we do have a discontinuity. If x is 0, then this isn't defined, but 0 is part of my interval. So when we're looking at this, my interval goes from 0 to 1. I'm trying to find the area underneath the curve here, but at 0 I know I have some sort of asymptote, so my function probably does something like takes off to infinity. Let's see, at 1 it just comes over here. I think at 1 it's at 3. That's how high it is. So I'm trying to find the area under here, but we have this infinite zone, this infinite region up here. So what we do is because our interval is to the right of 0, then when we come in this way, we're going to have to set up our limit as follows. The limit as t approaches 0 from the right side, so a little plus symbol there, of the integral from t to 1 of 3 over x to the 5th dx. So replacing the 0 with t, and then at the end we'll let t go to 0 from the right. So antiderivative there. This one hopefully doesn't require much thought. There's our integral. We just use power rule on this, so add 1 to that, you get -4, so it's going to be -3/4 x to the -4, or -3 over 4x to the 4th. That's your antiderivative. So this becomes limit, let's see, limit t goes to 0 from the right of the antiderivative of that, which is -3 over 4x to the 4th, evaluated t to 1. And that equals limit t goes to 0 from the right of, and then we'll have our two pieces here. So let me plug 1 in first. So 1 into there would be -3 over 4, that's it. And when I plug in t, I get -3 over 4t to the 4th. So now if I let t go to 0, this right here is going to turn into a fixed number on top over something that is heading to 0. And anytime we have a fixed number on top over something that's heading to 0, this thing is going to be heading to infinity or negative infinity, or the limit could not even exist. It does not exist. So either way you look at it, if it turns out to be positive, negative infinity, or does not exist, we can conclude that this limit, or this integral, is going to diverge, because we need this to go to a number for us to have an answer. So the answer is diverges because of that. see here. 25. Integral -2 to 14 of dx over the square root of, oh no, sorry, fourth root of x plus 2. So let me draw my interval here. -2 to 14 is where we're looking. But you can see here that if I plug in -2 here, I'm going to get 0, and that's undefined. So I know I have a discontinuity here. So again, it's doing something like becoming infinite here, and we have an area. Over here, it's going to be finite. Let's see if we can figure out what it is. 14 in here, 14 plus 2 is 16. And then you get the fourth root of 16, which is 2, so it's 1/2, something like that. So it's doing that. So we have area here, but then that one becomes an infinite region. So let's see if this converges or diverges. This is going to be approaching -2 from the right. So I'm going to have limit. T is approaching -2 from the right of the integral t to 14 dx over fourth root x plus 2. So I'm going to have to figure out what that antiderivative is, so I'll work on that over here. I need the antiderivative of 1 over fourth root x plus 2 dx. Basic u sub here. And I can rewrite this integral as 1 over the fourth root of u du, which is integral u to the -1/4 du, which turns into, adding 1 to that, you get 3/4, so flip over 4/3 u to the 3/4, which is 4/3 x plus 2 to the 3/4. So this becomes now this limit, and then the antiderivative of this evaluated at the two endpoints. So I'm going to just save myself a little time here. It's this, and then 4/3 x plus 2 to the 3/4 evaluated t to 14. This will equal the limit. T goes to -2 from the right of, and then now my two pieces. All right, so we plug in 14 first. So 14 into here, we get 16. 16 to the 3/4 is the same as the fourth root of 16 cubed. The fourth root of 16 is 2. 2 cubed is 8. So this is 8, right? When we plug in 14, we get 8 here. Then times 4. 8 times 4 is 32. 32 over 3. And then we plug in t. So replace t in here. We get 4/3 t plus 2 to the 3/4. And now what I need to do is let t approach -2. So if I let t become -2, this right here becomes -2. -2 plus 2 is 0, and 0 to any power should be 0. The only thing I have to pay attention to is that I'm approaching it from the right. And the reason that's important, I guess, is because if you come in from the right, you're looking at numbers like -1.99999, that when I put something like that in here, I'm going to get a very, very small positive number. And that's good because I'm going to be taking the fourth root of it. So if I'm taking the fourth root of a very small positive number, then that's possible. If I was coming in the other way, and this would be like -2.0001, let's say, then when I plug that in here, I'm going to get a little negative number in here, and I cannot take the fourth root of a negative number, so I wouldn't be able to do this. So that's why the one-sided limit is important. But because I don't have to worry about it, this is going to be 0, kills everything off. So the only thing left is 32 over 3. Oh, the answer is 32 over 3. All right, so this problem is a little different than the ones that I've done before because if I plug in 9, there's no problems here. If I plug in 0, hold on, that can't be all right. Is that right? X minus 1. Oh yeah, okay. If I plug in 0, there's not a problem either because I can take the cube root of a negative number. That's okay. The only issue I really have is if this denominator here is 0. So if x is 1, I have a problem. And 1 is in my interval. So looking at my interval, here's 0, here's 9. Right? The problem I have is right here at 1. I have this discontinuity. So the function's doing something where it's blowing up on one side, blowing up on the other. And I need to figure out if the area in here in this region is going to be finite or not. So what I'll do is I'll have to first split this integral up into two pieces, 0 to 1, and then 1 to 9. And each of these is going to be a limit. So limit, so 1 is where I have the issue. So I go limit t approaches 1. And since this integral represents this first side over here, I'm approaching 1 from the left side, so 1 from the left of the integral 0 to t 1 over cube root of x minus 1 dx. Then plus another limit, t is approaching 1 this time, so I'm working on this one. 1 is where the problem is. This time I'm on this side, so I'm approaching 1 from the right of the integral from t to 9, 1 over cube root of x minus 1 dx. Now, I need to figure out what that antiderivative is. Integral 1 over cube root of x minus 1. This is a basic u sub. U is x minus 1, du is dx. This becomes integral u to the negative 1/3 du, which is going to be 3/2 u to the 2/3, which is 3/2 x minus 1 to the 2/3. All right, so now I'm going to rewrite these limits. Or, yeah, these integrals which involve limits. So this first one becomes limit t approaches 1 from the left of the antiderivative of this, which is 3/2 x minus 1 to the 2/3, evaluated from 0 to t, plus limit t goes to 1 from the right of 3/2 x minus 1 to the 2/3, evaluated this time from t to 9. All right. This is limit t approaches 1 from the right, from the left, I'm sorry, of two things here. Let's see if I can squeeze these in right here. I'm going to plug t in first, which doesn't change anything. T, sorry. Then I'm going to plug in 0. So that was the first piece, minus when I plug in 0, I get negative 1 here. Negative 1 to the 2/3 is the same as the cube root of negative 1 squared. Cube root of negative 1 is negative 1, but then squared I get 1. So that's going to give me a 1 there. And then, sorry, then I had a 3/2 in front. So 3/2. I need to figure out what that is. Then this one, limit t approaches 1 from the right of, again, now I'm going to plug in two things. So let's try 9. 9 in here. 9 minus 1 is 8. 8 to the 2/3. 8 to the 2/3 is the cube root of 8 squared, which is 2, squared, which is 4. And then I multiply times 3/2. So 3/2 times 4, let's get 6. So when I plug in 9, I get 6. And then minus, now I plug in t. When I plug in t, I get 3/2. T minus 1 to the 2/3. All right. Let t go to 1. If t goes to 1, this is 0. That whole thing's gone. Over here, if t goes to 1, this is 0. The whole thing's gone. So I'm getting negative 3/2 here. Over here is 6 plus 6, which is going to be, see if I can do my simple math here, negative 3/2 plus 12/2, which is 9/2. I feel like I got that answer earlier for a different problem. I guess not. All right, 27's done. Hey, Zach, didn't you say you wanted to do problems today? Like you just wanted to get up and do problems?
I'm trying to get back into thinking mode.
Okay.
I'm going over the videos for the homework for 6.3.
Okay.